I started the recording. Attendance is really poor actually. Attendance is a big problem. Attendance is basically exactly half of the number of registered students. I think there are about 155 students and we have about 78 students attending. This is a problem. This is going to be a problem in future. Anyways. So after some instructions, verbal instructions from the administration, we are not really being tough on attendance because many students are facing many issues, but you will be those of you who are missing classes, you will have trouble later on because I would not be there to explain if you have any queries, even if you look at the video or lecture recordings. Anyways, we were studying Go Back N ARQ. Go Back N ARQ is a better pipeline version of an ARQ protocol. It is an improvement over stop and wait. It allows multiple frames to be sent out at one go, depending on whether those frames are in something called a window. Okay, the window size is defined and those frames can be sent out. The only issue is that frames can only be sent out and can only be acknowledged in order. If things are happening out of order, then retransmission takes place from the transmitter. Okay, from the sender. If suppose it has not received any uh, acknowledgement for a long time, it sends all the frames that it has sent since the frame for which acknowledgement was not received. For example, in this diagram, among the light blue colored frames, if the acknowledgement for base has not come back within the expected amount of time, okay, a timeout happens, and then because it has sent out this 8 packets starting from base up to a limit, this number, okay, up to maybe base plus 7, it sends out all these packets, all that has been sent out. And so this at the receiver, if multiple packets come, multiple packets in a sense that repeated duplicated packets come, those are rejected. But acknowledgements always happen, even to duplicated packets. Okay, so this is an important thing. Again, we will discuss later on this thing. Now, the question is, there is a bound which we yesterday's class we did not discuss on if your sequence number varies from 0 to max sequence. Okay. Then there are max sequence plus 1 distinct sequence numbers. That is easy to understand. Okay. For example, if your sequence numbers varies from 0 to 7, then there can be 8 distinct sequence numbers. Now, then the maximum number of outstanding frames, which is also equal to the window size, is actually max sequence and not max sequence plus 1. This is a mistake that can be made, but you have to be careful. We will now see with 2 examples what happens if you respect this limit, if you do not respect this limit, and then if you respect this limit. Okay, first you suppose you do not respect this limit. So your max sequence is 3. Max sequence plus 1 is 3 plus 1, 4. And your window size is also 4. Your window size actually should have been 3. It is above the stipulated upper limit. Let's see whether this works. Well, look at the sender and the receiver. The issue is that sequence numbers will kind of, after the max sequence value is reached, they will again start from 0. Okay, so this happens in any integer, finite bit integer arithmetic, you know that. Now look at what is the effect of making the window size 4. So this is a very unfortunate situation, but it can happen. It's not that it is impossible to happen. It can happen where every acknowledgement is getting lost. Okay. So frame zero is sent, a segment zero is sent, it reached the receiver, but its acknowledgement was lost. Then frame one was sent, frame two was sent, frame three was sent, everything was sent, and all its acknowledgements were lost. Okay. Now, please understand that the receiver has no way of knowing whether these acknowledgements are reaching the sender or not. In this respect, it is an asymmetric connection. The sender expects acknowledgements for any packet it has sent out earlier. But the receiver's duty is limited to the fact that it will acknowledge the successful receipt of a packet. Either it will collect the packet in its window, or it will reject the packet, but it will acknowledge that I have received something from you. But there is no acknowledgement to acknowledgement. Okay. Acknowledgement is the end of the story. So when these acknowledgements to 0, 1, 2, and 3 do not reach the sender, the receiver has no way of knowing what exactly is happening. Now, what happens is, after sending out all these frames, 4 frames, finally frame 0 times out at the sender. Sender says, oh, I have not received anything from about frame 0. Let me retransmit frame 0. So that retransmission will happen. Notice that the window has not progressed beyond the initial position because it has not received any acknowledgement for frame 0. So it retransmits frame 0. Unfortunately, this sequence number 0 to the receiver side looks to be a new frame. Please remember that receivers do not compare the data content of the frames to figure out whether this is a new frame or an old frame. The only thing they look at is the sequence number. And this time they find that the sequence number is 0. Okay, so it thinks that, oh, okay, so this is a new frame because anyway, the next sequence number, expected sequence number was going to be 0, right? So this creates a problem and it accepts the frame. The problem is it has accepted the frame. This is the problem because now this is the start of a new window, basically receive window with again 0, 1, 2, 3. In this way it will proceed. Do you understand, students, what happened, the error that happened here? That this is actually an old frame, but the receiver has accepted it thinking it is a new frame and it has placed it at the beginning of the new starting receive window. Do you understand? Any question about this, students? Anybody has any question?
So this can be avoided if the timeout time is decreased.
Yeah, but the timeout time decrease, how much will you decrease? You have to give certain amount of time. See, another problem with timeout intervals is it is not predictable. Okay. So you decrease it, but even then this type of things can happen. The transmission time can vary widely. Okay. It can vary by huge amounts, by factors of 10 or so maybe. For a short duration of time, within a short duration of time, it can vary widely. This is the problem with the network, with the transport layer. The transport layer, again, please remember, is trying to hide the deficiencies of the network layer which is below it. The network layer does not provide any delivery guarantee. It does not provide any maximum time upper limit guarantee, nothing. That we have introduced this timeout upper limits. This is the decision of the transport layer. The network layer has not told the transport layer to impose these limits. The retransmission is a decision or a policy taken by the transport layer. Okay, network layer has said, I will not give you any guarantee. I will neither give you a guarantee that at all whether I will deliver. I will not give you a guarantee of within what time I will deliver, nothing. And the transport layer has made very difficult to keep promises to the application layer saying I will give you all this service. This is the problem there. So basically we are studying schemes to address the deficiencies of the network layer. Most of the things that we are going to study in today's class, you will understand when your insight about the subject develops a little bit, that most of the design decisions or the policies of the transport layer is essentially to hide the deficiencies of the network layer. Now let's see what happens that if the window size is made according to the stipulated or suggested upper limit. So max sequence is 3. Okay, which means sequence numbers can vary between 0 to 3, 0, 1, 2, and 3. But now the window size is 3, not 4. This makes a huge difference because even if this same thing happens, now packet 0, 1, and 2 will all have reached the sender perfectly, but all its acknowledgement suppose was lost. But now when 0 times out at the sender and 0 is sent, at that point of time, the receiver will discard it because 0 is not within its stipulated window. Okay, it was not expecting 0. It was expecting something of sequence number 3. Sequence number space has not exhausted yet. Okay. And in its stipulated receive window, the first number expected is 3. So when 0 comes, it says it is rejected. Okay. Regarding your suggestion about decreasing the timeout interval, the problem would happen is that if the situation of the network improves or the situation, with very short timeout intervals, the sender would become too anxious and it will try to send packets too fast, retransmit packets extremely fast. So it has become so demanding that, okay, within 1 millisecond, I should get back an answer. But it will not happen in 1 millisecond. Your network is going to take time because the network probably has now become slightly slow serving. The network effective bandwidth has decreased. It doesn't get an answer within 1 second. Immediately it retransmits. Okay, so that is bad. Okay, so it is not a very good solution to decrease the timeout interval. In fact, this timeout interval estimation of round trip delays based on which the timeout interval is based. These are the topics that we will study for TCP later on in detail. Selective request we have studied. They allow the sending and receiving of segments out of order. Okay. So now in the sending window and the receiving window, out of order packet sending and receiving can happen. To support out of order packet sending, the receiver receives the segments and it sends an explicit negative acknowledgement back to the sender saying that I did not receive this packet, please send it to me. And then the sender again retransmits only those segments for which negative acknowledgement was received. Please understand one very important point. The receiver, although it can receive segments out of order, for example, here in this example, okay, in the receive window segment 2, so this is the segment sequence number varies between 0 and 3. So this is a 2-bit sequence number like the previous example. In the receive window of size 2, why 2 we will study very soon, because there is a similar limit on the receiving windows, window sizes also. This receive window is of size 2. In this, it has received 3, but it has not received 2, so it sent a negative acknowledgement to retransmit 2. Please understand that although it has received 3, it will not send 3 up to the application layer immediately. Why? Can anybody answer?
To maintain the order.
Yes, because again, look at the promises that the transport layer has made to the application layer. Let's see. Ordered packet delivery is one of the promises that the transport layer has made to the application layer. Okay. So even if, although it has received packet number or segment number or frame number, whatever you want to call, we should call it segment number actually. Although it has received segment number 3 here, it will not immediately transmit. So what should it do instead of immediately transmitting? It should wait. It should wait for 2 to come in. When 2 comes in, it sends both the packets, both the segments 2 and 3 to the application. So receiving of segments in an application is bursty. It doesn't happen in a smooth manner from the transport layer. Similarly, the rate, the generation of segments from at the sender from the sending application also is bursty and sporadic. It also happen in a continuous, smooth flowing manner. You should understand this, that the generation of segments to the sending window is bursty. The transmission of segments across the network is bursty. It does not happen at a constant, smooth rate. The rates vary widely, even in short intervals of time. The rates can vary widely. And on the receiver side, the final delivery of the segments from the receiver window to the application is also not smooth. It is also sporadic, partially because of the sporadic nature of the network that lies between the sender and the receiver. Okay. Now, a similar limit on the maximum window size exists for the bound exists for selective repeat also. So even if the maximum, if the sequence numbers are between 0 and something called maxic, okay, max sequence say, so then there are a max sequence plus 1 number of distinct sequence numbers. Then the maximum number of outstanding frames, which is also the maximum window size, can be max sequence plus 1 divided by 2. Again, for example, if there are 3-bit sequence numbers, which is the sequence numbers are between 0 and 7, both inclusive, then the maximum number of outstanding frames can be 4. Okay, so maybe I can just add max here. Let's see examples of situations where the limit is respected and the limit is not respected. Suppose first max sequence is 3. In that case, max sequence plus 1 divided by 2 is 3 plus 1 by 2, 2. But this guy has decided that I'll be aggressive and I'll keep my window size to be 3, which is 1 above the stipulated limit. Again, that pathological situation where those segments in the sending window was being sent and nothing was getting, I mean, no acknowledgement was coming back, all acknowledgements were getting lost. That can happen. So window size is 3, so you sent out 0, 1, 2 in sequence. Okay, no acknowledgement comes in. 0 times out, 0 is sent again. The problem is that because on the receiver side, because of your choice of the window length, receive window length, okay, 0, 1 and 2 have all received perfectly. Now when 0 comes in, it thinks it is the 0 corresponding to the new window. And remember, in the new window, it can now accept packet segments out of order because this is selective repeat. Okay. So now it thinks this 0 is a new segment and it accepts the segment and puts it in a slot of the new window 0. Okay. Which is not correct. This is an old segment. This was actually an old segment. So this is a mistake that the receiver is making. Any difficulty in understanding these examples, students? Anybody has any question? It's a very nice example. Notice that, I have one more question. Would this problem had happened if there was, if this was go back in 3 and 3, there would not be any problem, right? Just now we saw an example. There was no problem here. So selective repeat gives you more freedom to send and accept packets out of order, but it comes at a cost of your decreased window length. Okay. Anybody has any difficulty in understanding why this failed here? Or this example? No, so I think you have understood it. Now let's see a window size where the window size respects the sequence number length limit. So again, max sequence plus is 3, max sequence plus 1 divided by 2 is 2, which should be the maximum window size, and I have now kept it 2. When you keep it to be 2, 0 and 1 can be transmitted because they are in the sending window. Both were received, but nothing got back. No acknowledgement got back. So 0 timed out at the sender, 0 was sent again. This time 0 is not in the stipulated receive frame. The receive window. The stipulated receive window should expect frame numbers 2 and 3. Because 0 came, it rejects 0. But of course, it will send back an acknowledgement, and it will discard the frame, old frame. So you should note that duplicate frames are discarded, but an acknowledgement with the frame number is sent back to the sender so that the sending window continues to slide forward. In this case, in TCP, what will happen is it will send back an acknowledgement saying that I expect now frame number 2. Because it is a cumulative acknowledgement, okay, the sending window understands, oh, he is now expecting 2, which means he has actually received 0 and 1. So earlier he has actually successfully received, I was not getting the acknowledged signals. That's why I retransmitted 0, but okay, fine. He has received 0 and 1. Okay, now let's move my window forward to 2 and 3. So it will jump the window. I mean, the window will jump directly to 2 and 3, and then it will send 2. Okay, you understand, students? Again, any question? Any observations? Any suggestions to improve this? Or any insight that when this might be get into trouble, this scheme? Fine. So let us move. Now, one very important. Yes.
Sir, does the jumping always work? If the size was greater than window size was greater than 2.
No, window size was greater than 2. Jumping will not work. The worst thing is packets which are not in the correct sequence will be old packets might be accepted as a new packet, like this example showed here, that the window size was also 3, which was above the stipulated limit. Okay, so this was stipulated limit plus 1. So an old frame was thought to be belonging to a new to the current receive window, and it was accepted out of order.
Okay.
So this is completely wrong actually. Okay, this will not work. So I'll just mention that. And did you understand why the acknowledgement will now in TCP always works with the next expected frame number, this convention. Why the sender would now, when it receives 0, it will discard 0, and why it will now send an acknowledgement with number 2, because 0 and 1 it has already received. Okay, in fact, it will send an acknowledgement with next expected frame number 2 also in this case, the second acknowledgement for 1. But that didn't reach. But again, it will send the same thing, that my expected segment next is segment number 2. When that, probably this time it will reach the sender, that time he understands that 0 and 1 has been accepted, has already reached the receiver. That's why he is now saying I want segment number 2. So he stops bothering about 0 and 1 and pushes his window forward by 1 go, and the window now comes to 2 and 3. Okay.
Okay.
That's why it's a sliding window is more effective than stop and wait. Stop and wait always it proceeds the window by exactly one at a time, one step at a time. Whereas sliding window, if everything goes well, a chunk or a collection of n packets will reach the receiver. You will receive a cumulative acknowledgement for everything, and your window will shoot forward to the right by n locations, n spaces. Okay, so right shift by n places, new n frames are ready to be sent when they are available from the application layer. So that's why it's a pipeline and it is so effective and efficient.
Sir?
Yes.
So how does sender and receiver agree on the same window size?
No, they need not agree. I will come to it. Well, it need not be exactly the same. I mean, you are saying what should be the, how do they agree, or whether it should be the same, or I think window side is the same, but the value is not constant. TCP, whether it will allow window size. Window size is a parameter, okay, which basically determines the what should be the window size. It is proposed by the person who starts the connection, I think. So actually, they continuously update the window size depending on what the other side tells it to do. Okay, so it is not it need not be constant actually. For initially they agree on something, but it can keep on changing over time. Okay, the other side says that you set your window size to this and let us use this window size. And but this keeps on changing. When we study TCP, it will be clear. And there is a mechanism, there is a field in TCP segments to set it. Okay. So this is set by mutual understanding by transmitting messages. I mean, those are not separate messages. Those are fields in the TCP segments. Now let's come to another very peculiar thing. Till now we have studied that sliding window is good, stop and wait is bad, but if you have to understand that not all links are very good links. Okay. So there is something called a bandwidth delay product. This actually kind of restricts your overall performance. For example, say your bandwidth is relatively on the low side, say 50 kbps. One-way transit time delay. Currently, this one-way transit time delay is not constant. In the network layer, nothing is constant. Okay. This is not like a dedicated telephone connection where more or less the transmission time between you and the receiver is, if it's a continuous copper wire based connection, more or less you can get a fairly good estimate of what should be the transmission time. Okay, because electrical signals transmit over conductors at kind of fixed speeds, and from the material you can calculate that. So what is the length of the copper wire in between you and the receiver? If it's a landline telephone connection, from that maybe you can calculate. This is not like this, unfortunately. I mean, this doesn't work like that. IP networks do not work like that. Okay. So currently, suppose the one-way transmit time is 250 millisecond. Then you multiply the bandwidth with the transmit time. So suppose 1000 bit segment size means the bandwidth delay product is approximately the length of 12.5 segments. Okay. Now, acknowledgements will come back for every segment. Okay. So this takes a further round trip time. Okay. So twice the one-way latency. So the maximum number of segments that can be outstanding during this duration is 12.5 from the receiver side and 12.5 from the sender side, which is approximately 13 segments, 25 segments. But the first acknowledgement is sent only when the first segment is received. So it increases by 1. So 26. Okay. So this is the maximum link utilization. If 26 segments are in transmission between, on average, between the sender and the receiver, you are utilizing the network to the available bandwidth to the fullest, given that delay. Okay. Bandwidth and delay are slightly different things. Okay. Bandwidth is how much data you can send, and delay is a measured parameter of how much time is it taking for the signals to go from one point to the other. Their product is kind of the total amount of data that is pending, hanging in the network, corresponding to a particular connection between two parties A and B, say. Now, if BD is the number of frames equivalent to the BDP and W is the maximum window size, then W is 2 BD plus 1. Okay, so this is kind of the maximum window size in terms of the BDP. This, if you set the maximum window size to 2 BD plus 1, this gives the maximum link utilization. So this is what TCP tries to do. It continuously evaluates and measures the round trip time or the based on its timer based thing. It sees how much time is it taking to get the acknowledgement. From that, using certain formula, it is, well, it's not very straightforward how it actually estimates the round trip time. Round trip time is just not one measurement. Okay, please understand. Round trip time is an average over several measurements. And how to calculate the average is just not a simple arithmetic mean. It is something else. We will study that. Why? That also we will study. Not in today's class, later on. It keeps on estimating and updating the round trip times. Okay. As it keeps on estimating and updating, okay, and it has some estimate of the bandwidth. Based on that, it sets this this thing to 2BD plus. It tries to set it to this value, around this value. Okay, it cannot set it to exactly this value, but around this value. This is to show you that the window size, just now somebody asked the question, how do they agree on this window size? They agree through message transfer exchange between them. These messages are not separate messages. These messages are superimposed on normal messages. And they keep on changing this. The more important concept is that this keeps on changing over time. Even for the same connection, it can keep on changing if it's a long connection. It's connection for a long interval of time. Okay. Now, let's see. Now, suppose the link bandwidth is reasonable. 1 Mbps is not bad actually. Okay, 1 Mbps is, well, cannot be said it is that bad for ordinary connections. Of course, it is not in gigabit Ethernet or those kind of things, which is like 1 Gbps. But 1 Mbps is hardly, I don't think anybody, I don't think for wireless, etc. connections, 1 Mbps is actually quite good. Now, suppose the segment size is 1 KB, again quite reasonable. 1 KB is 1024 bytes. Suppose the delay between the two parties is 1 millisecond. Okay. Which of the protocol is better? Stop and wait, go back in, or selective request? All of us, we will very enthusiastically say, hey, stop and wait is bad. It has very bad throughput. Go back in and selective request should be your only choices to go. Probably selective request. But please understand that the window sizes have certain limits. Okay. What happens if you calculate the bandwidth delay product? Your bandwidth delay product now is 1 kilobit, 1024 bits, and your segment size is 1 kilobyte. 1 kilobyte segment is a very, very, very reasonable length, probably a little bit on the smaller size. Okay, it could have been larger probably. Okay. Now, just one segment is 8 times larger than the BDP. Okay, just imagine the BDP is so small that your link cannot even hold one segment completely. So what is your window size? I mean, how does it matter? And you are saying we will have go back in and selective request where there are very large, might be very large windows. We will have very large windows. Then we will have great throughput. I mean, what are you talking of? Here it is so bad that the link cannot even hold one segment completely. And then you have a limit on the window size that is 2BD plus 1. Okay. So basically your maximum usable window here is kind of 1, but then you are going back to stop and wait. So in this case, stop and wait is better. You want to try to use sliding window forcefully in this poor situation, poor bandwidth delay product, your performance will be miserable. You will send out plenty of packets at one go. All of them will collide with each other because they will not reach the receiver within time. And you will not get back acknowledgements for most of them. You will retransmit again and again and again. Selective request is go back and is horrible. It will retransmit many packets. Okay, so you will be in big trouble. I mean, it will be horrible. So say sliding window does not always improve performance. Okay, that's the moral of the story. You have to first think Why are we still studying stop and wait in spite of sliding window protocols being in existence? Reason we are studying is that stop and wait is not a useless concept. Okay, it still has value. This is kind of similar to computer architecture. You have pipelines, 5-stage pipelines is what we probably studied if you have taken the course last semester. Somebody can think of 20-stage pipelines, but does it really help? Well, there are 10-stage, 12-stage pipelines in the market in commercial products, but those are specialized. Probably the floating point unit might have 8-stage or 10-stage pipeline, etc. But general extremely deep pipelines in the general instruction execution unit, I don't think is very common, because there are many other issues that come in. Power consumption increases, your pipeline registers take up more area. If there is a issue, if there is a hazard, then your lot of clock cycles are wasted, etc. And to improve that situation, you have to do superscalar pipeline design, which makes the design even more complicated, etc., etc., and it keeps on increasing. Okay. So stop and wait is better because it has less complexity, and in poor BDP situations, it gives better design. Now let's see what happens the sender side and receiver side. How does it work? Consider some hypothetical API calls called write and send from the user application, which sends data to some buffer pool in the kernel. This is called a transport buffer on the sender side. This buffer pool is a collection of buffers. Okay. The segments wait in the buffer pool. Periodically, another entity called tport send. This is also an hypothetical name, but this, depending on the transmission rate control mechanism, which determines that now it is a good time to send out something, it periodically triggers the transport send utility, and then it passes on data to the bottom layer. Okay, to the IP layer, which takes care of forwarding it further. Okay, so this write clock call will block the port until the complete data that is supposed to be written from the application is written in the transport buffer, provided there is space in the transport buffer. Okay, how much space is left is an important issue. If the application is generating plenty of data, everything cannot be sent to the transport buffer at one go. Okay, some will be sent, then probably you'll need to wait, send out stuff from the transport buffer, then again send stuff from the application to the transport buffer. Please understand that the transport buffer cannot immediately get rid of all data. Okay, you need to hold the data for some time. In any sliding window protocol, you only move the window when you receive acknowledgements, the necessary acknowledgements, then you are allowed to slide the window forward. So immediately you cannot just say that, oh, okay, just I have sent out the packet, get rid of it. You cannot do that. You have to hold it for some time. Similarly, on the receiver side, there is suppose an entity called transport receive, which receives data from downwards from IP from the network layer, and then they are separate transport buffers for different user applications. Okay. It checks the buffer. There is a mechanism to check the buffer periodically. When it finds that there is some stuff in the buffer which has to be sent to the application, it interrupts. The application need not keep on hearing all the time to the this reading mechanism. Okay, or to the maintenance connection with the kernel. Through an interrupt mechanism, it can wake up the application and say that some data is waiting for you. Please come and take it. And for the time period when the application reads the data, it blocks. Okay, and the complete data after it has been read, it releases this connection between the. It does not block. It goes and performs other things. Okay. So this is how this keeps on working. Now the question is that this interrupt thing, it can also be implemented either as an interrupt mechanism or polling mechanism, where periodically you poll the buffer to see whether there is something. Okay. You ask the poll buffer utility, please check the buffer at some intervals, maybe at periodic intervals, exact periodic intervals, or maybe not. But I mean, interrupt driven things are probably better because there is an overhead associated with an interrupt, but this polling mechanism, if nothing is coming from the other side, this polling most of the times will not find anything. So this is a wastage of effort. Interrupt, on the other hand, will only disturb you when there is actually data available for you. Okay, so that helps. Now the question is, how will you organize the transport buffer pool? Okay, so there are many options. First of all, if your segment size, you know that the segment size are more or less fixed. So one implementation is kind of a linked list implementation. This is called a chained buffer implementation, where you decide that, okay, my each buffer size is going to be some maximum segment size, and I organize my entire available buffer pool memory. Maybe say, I'm just giving a random example, say 500 megabyte. Okay, 500 megabyte of space. Everything will be in terms of this equal size chunks. Okay, if every chunk is 500 kilobyte, then I will have 1000 such chunks, something like that. Okay, that many segments can be held in the send and receive buffer pools. But there are two issues with this. One of them is that the maximum segment size you want to bake, but there might be segments which are not the maximum segment size. The maximum segment sizes are quite large. Later when we study TCP, the allowed maximum segment sizes are quite large. TCP rarely uses that large segment sizes. Okay. Okay. It rarely uses very small segment sizes. Those are used, but very rarely. But it also rarely uses very large segment sizes. It kind of stays in between. So if you have already pre-decided that all my buffers are, every buffer is going to be the maximum allowed segment size, and you have organized your collection of buffers, that is buffer pools, in terms of that, then when you are not using segments which are of the maximum size, you are wasting space. Okay. Also, if you are using very small buffer sizes, then what will happen is then multiple buffers will be required to store only a single segment. Say your average, most segments are kind of in the order of 1 kilobyte, and you have decided my buffers, each buffer is very small, each buffer is only half kilobyte. In that case, two buffers will be required just to store one segment. And the segment as an organization, segment is just not data. Okay, segment has many other things. There is a substantial amount of data, metadata present in something called a header of a segment. When we study TCP, we will study the segment format in detail. It's quite complicated. Okay, so now you will say that nice organized data structure, I will now divide, give part of it to one buffer, part of it to another buffer, then I will link list them internally, then I will link list them with other such segments. I mean, this is a big headache. Okay. So next option is, you say, okay, fine. Whenever a segment comes, I will decide what is the size of the segment. Dynamically, I will create, allocate a memory which is of that length, and then I will connect it. So now you are saying that, well, you see my buffers will now be of variable size depending on what segment I need to send or receive. But then, well, again, there can be issue of unused space. Okay, because probably you will still need to go for some amount of granularity in your discreteness in your size. Sizes cannot be exactly arbitrary. For example, say you allow variable size segments, but in intervals of either 1 kilobyte or 2 kilobyte or 3 kilobyte. But then if something is 2.5 kilobyte and you have allocated a 3 kilobyte segment, then 0.5 kilobyte is wasted. And also this complication of implementing variable size buffers has to be taken care of. The other option is to implement a large circular buffer where the first segment, then there is a delimiter with some information, then the second segment start, then the third segment start, fourth segment starts, etc. And these unused spaces are there at the end. Nothing is wasted because now the unused space at the end of the circular buffer, this can be assigned to other segment also, another segment. And this is a circular buffer. So if that thing does not hold here, it can, if necessary, it can go back and occupy something towards the beginning. If in the meantime segment 1 has been freed. So this is a circular array kind of an data structure, relatively good use of memory. But this works better when all the connections are heavily loaded. Okay. Otherwise, the memory usage is not very good because you are now saying that my entire memory is already allocated for the array. Circular array, if you remember, the total length of the array that is statically already assigned. It's not like dynamically you are keeping on allocating the arrays. How much space you are allocating in certain location of the array, that is a dynamic decision that you have to take depending on the segment size. But initially everything is allocated at once. But then if so many segments are not coming, you are sitting with 100 megabyte of space in a large circular array and it is only occupying 1 megabyte because it's not a very heavily loaded connection. So all these practical issues, programming issues remain. Okay. Okay. So, okay, dynamic buffer management will continue. Let us take a 2-minute break, 2-3 minute break. Okay, I'll come back in a few 2 minutes. Okay, let's continue. Okay. Now the question is that the buffer sizes, okay, these have to be dynamically adjusted. This is a very important concept. Okay. The sending rate by the sender transport entity and the receiving rate of the receiving transport entity, okay, or receiving, sorry, sending rate, the generation rate, okay, of the segments by the transport entity on the sender side, which is this one, okay. This depends on at what rate this application is generating data, okay, and also at what rate it is being able to send out this data depending on the transmission rate control mechanism, which is dependent on the situation of the network. It is not entirely under the, it is not under the application's control. So there are two different parameters or two different agents in play, independent agents, which determines at what rate data will accumulate in the transport buffer of the sender. One is the rate at which the sender application is generating the data, and the other is the rate at which the transmission rate control mechanism is allowing data to be sent out. Similarly, at the receiver side, there are two different entities which control how much data is accumulated in the transport buffer on the receiver side. One is the rate at which data is being received from the IP layer or network layer. Okay. And the second independently is the rate at which data can be removed by the application. Okay. It will interrupt the application and say, please remove the data. But the actual rate at which the application will remove the data, that is whether it can immediately listen. See, all interrupts immediately cannot be paid attention to. If the application is in the middle of doing something important, it might not immediately pay attention to such an interrupt. Those are called maskable interrupts. Okay. So in that case, it will decide, okay, I will listen to you are asking for my attention, but please wait, I will listen to you later. Let me complete whatever I am doing. So during that period of time, the transport buffer should keep on holding this information safely for the application to collect it at some point of time later on, shortly. I mean, not very not like after 2 days or 3 days, maybe after 2 milliseconds, but for 2 milliseconds, it has to hold the data. Fine. So these, because of these independent factors at play, the window sizes are advertised by the two parties to the other side. It requests something. One side can request, please give me this window size. Means your window size space, I am requesting, give me this much. Because I am going to send out data that fast. I mean, so much data. The other side replies, no, listen, you are wanting like size 8 window. We can only give you size 4 window. Okay, I cannot give you more than that. You have to adjust and send out data properly so that you are not sending out data too fast, because I cannot support such fast sending of data. Then your packets will come at my end and I will not accept them because my buffer is full. Packets can be rejected at the receiver if buffers are full. Okay. This is an unfortunate situation, but this can happen. So no point asking for too much of space from a receiver on the receive window size when from the on the sender side. Saying the example is this, what actually happens. So through window sizes, they requests can be made. For example, A is kind of the sender and B is the receiver. So again, to make life simple, this is an asymmetric connection where A is only sends messages and B only receives and acknowledges. First, please pay attention to this very carefully. Okay. First, through some message connection has been set up, some data transfer probably has also happened, or it is towards the beginning. Okay, no, I mean data transfer hasn't yet started, just towards the beginning of the session. Connection handshaking, three-way handshaking has successfully happened and connection is set up. A sends a message. How this message is sent, we will study later when we study TCP. A tells B, please give me 8 buffers. Request 8 buffers means on your side you have 8 buffers. It is telling B. Okay, because on my side maybe I have decided to have 8, size 8 buffers. So B says, okay, A wants 8 buffers, but B calculates and says, no, I can only give you 4 buffers. Acknowledgement 15 means that the next expected packet number is 15. Okay. And it says buffer size 4. So this is piggybacked on the message. Okay, acknowledgement and buffer size is piggybacked. Then A starts sending. A says, okay, what to do? He says buffer so window size should be 4. Okay, I will also fix my window size to be 4 and I will start filling up my buffer as I receive from the application and try to send out this. So it starts sending out something here. Well, the acknowledgement 15 was used. Because these are 4-bit sequence numbers. Acknowledge 15 means probably message number 15 was done. This is not following again. This is not following a next expected convention. This is following a received convention. So I have received message number 15, but I am giving you buffer size 4. A is forced to fix its buffer size to be 4. Then it starts sending the messages starting with sequence number 0 because 4-bit sequence numbers after 15 0 comes. First data M0 is sent. Then M1 is sent. Okay. Now there are 2 spaces in the buffer. Why 2 spaces in the buffer? Students, can any of you explain this comment on the right hand side of step number 3 and step number 4? Anybody? Why A has 3 buffers left and 2 buffers left? Hello, can you hear me?
Yes, sir.
Yeah. So why does this comment say A has 3 buffers left and 2 buffers left? What do you mean by buffers left?
Sir, there's a number of free buffer spaces available on the internet.
Yeah, but the data segment M0 and M1 has been sent out already, right?
Right, sir. So A can now send 2 more messages before the receiver side buffer fills up.
No, my question is, see, M0 and initially buffer 0 is fine, but M0 and M1, these are being sent out, right? So why not A has 4 buffers left, even after sending out M1?
Acknowledgement may not be received.
Yes, very good. This is a sliding window protocol, okay, in general. Acknowledgement has not yet been received for either M0 or M1. So you have to keep on holding M0 and M1. Total 4 is allowed, of which you have sent out M0 and M1, fine, but you have not received any acknowledgement. Fine, finally it sends out M2, but unfortunately the message on its way was lost. Okay, now B sends a cumulative acknowledgement back to A saying I have acknowledged till 1. So I have received 0 and 1. and you can now send some others. Okay, and it is saying that I have buffer space, I have 3 left now only. You can only, I have only 3 spaces left now. Now, because permission was there to send some more, A sent out 3, then A sent out 4. Okay, and A has 0 buffers left. It must stop. Because why it is stopping? Because it has heard nothing about the acknowledgement of M2. M2, nothing was received. A times out and resends. That reaches B. B says, I have no buffer space, unfortunately, but I am acknowledging 4, which means I have received everything till 4, but I don't have any buffer space. Then suddenly it sends another message saying, oh, my buffer space has now increased to 1. Then it sends another message, my buffer space has increased to 2. Okay. So A, when it receives buffer spaces increased to 2, finally say A gets M5 and it sends M. It could have also sent before that, after 11 also it could have probably sent. But anyways, after 12 it got a new message, immediately it sent. It has 1 buffer left because it is kind of aligning its number of buffers with the receiver. So when it got M5, it immediately sent it. Then finally it got M6, it sent it. It can send 2. And then it is waiting. When will I receive back my acknowledgements for M5, M6? It is waiting. Now B sends back a cumulative acknowledgement saying, I have received up to 6, but my buffer space is 0. Okay, so A says, okay, everything that I have transmitted to it has been successfully received at B, but unfortunately this guy doesn't have any buffer space left. No point sending anything to him now, because if I send, then he will reject it. Let me wait, let him tell me that he has some space, he has found some space, then I will send. Now something very unfortunate happens. After 15, message number 15, whatever A sends somehow gets lost on the way. Whatever B sends, whatever the sender receiver B is sending back is getting lost on the way, because suddenly the channel has become very, very noisy. It is not reaching A anymore. But then one of the messages that B sent back was acknowledgement 6 buffer size equal to 4. So it got a lot of free space now. It has 4 spaces, 4 segments it has got. So it can receive, this actually the size is in terms of bytes, but say 4 bytes it has something. So it has some space, but unfortunately because these messages are getting lost on the way back to A is not getting the messages, and because A is not getting the message from B, it is not sliding its window forward, and because its last message that was successfully received said buffer size 0. And B is also not doing anything because B is not waiting for messages to come from A. So this is kind of a potential deadlock. Each of them is waiting for the other to perform something else to do, which can lead to a deadlock if messages are not flowing properly. So the acknowledgements are very, very important part of connections. If acknowledgements do not flow properly in a network, then this type of buffer size management issues might happen, and the situation can become really bad. Next, this was what we were studying, is a rate management between the two individual parties. Now, what happens in a global scale? Suppose S and D are trying to communicate with each other, source and destination. Okay. In between, there are so many routers, so many routes are there. Each routes have different delays. This entire connectivity can be modeled as a directed graph with certain weighted directed graph with certain edge weights. These edge weights are basically symbolic of the cost probably or the delay between the two routers. It can be symbolic of some other parameters also, but usually that is this is a common metric. Okay, so say for example, from S till the first gateway router, the weight is something like 50. Okay, in this way. So how can you maintain optimal flow rate? So you can apply a max flow min cut theorem. But this is, this is really hard in a real large network, because to have us, first of all, to have us idea of the complete network graph is kind of infeasible. It doesn't make much sense. The network has become so vast. And if you're talking of the internet, it's an incredibly vast network. Okay, routing along so many different routes are possible. Doesn't make much sense. There is no centralized control. Later on, when you study networking, you will find some schemes which try to do some calculations based on this model. They try to estimate, at least in its neighborhood, what is the situation they try to estimate. Okay, but it's quite difficult to do. So theoretically, you can say that, well, I will send all my packets along a route which will ensure that there will be maximum utilization of the links, and I will send my data packets along that route only because the max flow min cut theorem tells me that there is a limit of the maximum flow that can happen in a given network like this. Okay, so you can try to abide by that limit, but it is very difficult to estimate such a limit in a real graph. So what they do is basically the allocation of bandwidths have to be autonomous. So what happens is, ideally you try to give the entire bandwidth to initial flow, then another flow starts, you decrease the bandwidth a little bit, then another flow number 3 starts, you say, okay, I will decrease the bandwidth of this flow a little bit, then another flow stops, it again increases the bandwidth a little bit, etc., etc. The question is, who is going to increase and who is going to decrease? Nobody is sitting there, nobody is the big boss who is controlling everything. Okay, there is no super user in this network who will control all this. So the the most magical thing about this rate control entire subject is that the rate control happens more or less in autonomous ways. Okay, in an entire huge network like the internet, where depending on decisions that are made locally by each individual party, every individual party respects the current situation of the network, and accordingly it changes its sending out rate. It says, when it says that the network is very fast, it sends out data. Network is very fast based on its own experience, within what time it is getting back an acknowledgement, this kind of things. The round trip time is very short. That also, that metric also, it keeps on continuously updating. As and when it sees that the network situation is quite good, it sends out data at a faster rate. When it finds, well, many packets are getting dropped, I have to retransmit them again and again, or the round trip time has become horrible. Okay, I am getting acknowledgements after long intervals of time. Okay, then at that point, those points of time, it slows down. It says, okay, things are quite bad in the network. Let me be less aggressive. And this is followed by everybody in the network. The network is a shared resource, okay? The link between two routers, okay, cannot be given to the one party. So I will come to it. So this concept is called congestion avoidance, where each party tries to avoid congestion. Okay. So how can you avoid traffic jams in a network? Well, one of the ways is, of course, see, one of the things is, of course, if there are too many cars, nobody has control over the other person driving a car. Means you cannot say that I will drive my car, you don't drive your car. Everybody will drive his or her car. Everybody has to go to office. Students have to go to school. People have to go to workplaces, hospitals, wherever. Okay, so everybody will say, no, 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 I have a priority, I will go. So if the city does not have sufficient roads to support this, of course, there will be congestion. This is one way. But the second way is, you know that between this time and this time of the day, this road is particularly congested. You would say, see, there is a way to avoid this congestion. Either I will take a different route and avoid that road, or I will go at a different time of the day. I will not start my journey at that point of the day. This type of well-intentioned decisions by the individual agents is congestion avoidance. Nobody is superimposing, no traffic police is coming to your home and saying, no, no, don't start your journey now, start your journey after 1 hour, or don't take this route, take any other route. Traffic police sometimes in big cities do that, that this route is too congested, please take a different route. But in general, that is not the truth. And in networks, computer networks, it is impossible to implement. Okay, because every agent is kind of autonomous. So given the dynamic nature of this network and the fact that every agent is autonomous, our sending rate for a well-behaved agent has to be the minimum of the network rate and the receiver rate. Network rate is what I perceive. Okay. What I am perceiving as the rate which my network can support, and the receiver rate is what my receiver is telling me that please do not send me data at more pace. I would not be able to handle this. Okay, as a teacher, okay, I can say I will teach very fast, cover a lot of topics in one day. But I have to consider two things. If I teach very fast, the quality of my teaching will go down. And if I teach very fast, the students would not be able to absorb it at the necessary speed. So I have to come to a decision, look, I should not increase my teaching speed beyond this point, because that is going to adversely affect the quality of teaching and also the experience of the students. So I have to correct myself. Okay, this sending rate decision is implemented inside the TCP, part of the TCP protocol itself. So the TCP is well behaved for every party. The amazing thing, why I said that the amazing thing is that amazingly this works most of the time. That if everybody is well behaved, it will be more or less, it will be okay. Say in many Western countries, cars travel at very fast speed. Many more people have cars. Of course, there are more roads, wider roads, but also the number of cars are also quite high. Private cars, almost every family has one or more than one private car. Still, there are not too much of traffic jam, etc. Why? Because drivers are well behaved. They respect and obey traffic rules, which is not necessarily the case in many developing countries like India, where First of all, the number of roads, etc., especially in big cities or near big cities, is not sufficient. And secondly, drivers are very aggressive. They do not obey traffic rules, etc. So two different factors, the experience or the feedback received from the network and the feedback received from the receiver. These two factors determine the sending rate of the sender. The receiver sending rate is a one-to-one correspondence. I mean, one-to-one connection based information, particular connection between sender and receiver is that thing. The network rate is the kind of the global network information which everybody else is also participating in. There is a concept called good put. Good put is kind of good throughput. Number of packets successfully delivered per second. Okay. So if your capacity limit is this, the graph on the left hand side shows an ideal plot of how the load should increase. When it increases, reaches the capacity, it should stabilize and saturate. However, it doesn't happen like that always. Okay. Many times what happens is that the desired, so this is kind of very ideal, this type of sharp straight line kind of thing. This doesn't happen. The desired is like there will be a smooth convergence to the asymptomatic, like the asymptotic limit of the capacity. What can also happen sometimes in practice is something called congestion collapse. When you keep on increasing the offered load beyond a certain point, you find that, well, my I'm not getting the packets properly. Okay, I mean my throughput is not that good. Why is your throughput not good? Remember that is sometimes it is not your fault. Sometimes it is a fault of the underlying network between you and the receiver. Maybe for some reason the routers lying on the network between you and the receiver have become very busy. The routers are handling collection of connection, many different connections. They also have limited buffer capacity. Maybe their buffers themselves are overflowing. So your packets are not going through to the other side. So you are timing out. So you said, oh, my throughput is slightly falling. Good put is slightly falling. Let me send packets even faster. And you try to send packets even faster. Everybody does that. Everybody congests the network even more. And the throughput drastically decreases. Okay. So this is something called a congestion collapse, where many parties, they are in a desperate way, they are trying to improve the throughput by sending more packets out, but nothing is happening. In fact, that is worsening the situation in the network, and the good put for everybody would drastically collapse. Okay. So actually the offered load, as the offered load increases, it might happen that your delay kind of exponentially increases. Okay, so in the plot on the right, delay is on the y-axis, so it can happen your delay exponentially increases. It is good that we should try to have a fair rate in the network. It is very difficult to implement. What is fair rate? Fair rate is that given the total bandwidth, try to distribute it among the different flows. A flow is something, connection, data transfer happening between two parties. Okay, so that max min fairness is maintained. Max min fairness is something where the bandwidth given to one flow cannot be increased without decreasing the bandwidth given to another flow. Okay. An example is this. Look at the links and the actual amount of bandwidth being used. For example, every link here has a bandwidth 3. Most of the links there is a spare bandwidth. For example, between router 1 and router 2, R1 and R2, 1 unit of bandwidth is spare, only 2 is being used. Okay. However, between router 2 and router 3, there are okay, these are fractions. So consider that each of them has one unit of bandwidth, and 2/3 is being occupied between R1 and R2. Between R2 and R3, there are two flows. One flow is flow A, the other flow is flow B. Okay, so flow A is occupying 2/3, flow B is occupying 1/3. Now, interestingly here, you cannot change the flow of one. Say, for example, you decide that, well, see, between R5 and R2, there is lot of spare. I am only using 1/3 of the bandwidth. So let me increase it to 2/3. Okay, so between R5 and R2, I will increase it to 2/3 so that B increases. Okay, but the problem is you cannot increase it to 2/3 because if you have to increase B to 2/3, you have to decrease flows C and D by certain amounts. Otherwise, you cannot increase B. The sum total of the flows along the link between R4 and R5 is also 1. So if you make one of them 2/3, the others have to decrease. Similarly, flow between R1 and R2 has to decrease, because if this guy between R2 and R3 for B becomes 2/3, then the flow between R2 and R3 for A has to become 1/3, which means between R1 and R2 it will also become 1/3. So just because you gave additional bandwidth to B, you had to take away something from A. This is an example of a min-max, max-min fair allocation. Okay, whether this is perfect? Well, this is not perfect because there is spare bandwidth that is being unused. But at least given this situation, you cannot do better. This is the max you could have done, best you could have done for these existing connections. Now we come to a very, very, very important and interesting concept called how to find a fair operating point for congestion control. This theory has been explored by many people, but the work on which the TCP's congestion control is based was developed in a paper by Chiu and Jain in 1989. You can just give Chiu and Jain AIMD on the Google and you will find the paper. Okay, you will stay. The PDF is still available. This is called an additive increase multiplicative decrease scheme. Okay, this shows that how the sending rate is modified. WT is the sending rate at time T. What should be the next sending rate? T plus 1 does not necessarily mean at time exactly T plus 1 second. No, please understand that. It means what should be the next sending rate when I need to calculate it. Okay, so that might happen after 10 milliseconds, after 50 milliseconds, after 1 second, after 5 seconds, whatever. So in a discrete way, you should treat this T plus 1. Currently, let WT be the sending rate. Suppose A, which is a positive, is an additive increase factor, and B, which is also positive but smaller than 1, is a multiplicative decrease factor. Then, if congestion is detected, it increases sending rate by adding a constant rate to WT. And if congestion is not detected, and if congestion is detected, it decreases the sending rate by multiplying WT with a constant between less than 1, between 0 and 1. Additive increase, multiplicative decrease, AIMD. Okay, why did they suddenly choose this and it got so popular that it was adopted in a global standard like TCP? Well, let's see. suppose there are only 2 users. They established this in the paper through this type of plots and also a lot of mathematical arguments. So in this class, we will not go through the mathematical arguments because that is probably the topic of some other types of subjects like performance modeling of computer network or those type of subjects. We will just study the concepts behind this. Conceptually, what is the case? Please notice this graph. There are 2 different bandwidths plotted along the x-axis and the y-axis. The bandwidths are in terms of percentage, 0% to 100%, etc. So user 1 can have the bandwidth between 0 and 100% allocated. User 2 can also have a bandwidth between 0 and 100% allocated. If user 1 takes up the entire bandwidth, user 2 has nothing left, and vice versa. If user 2 takes up the entire bandwidth, user 1 has nothing left, and this is not desirable. So the optimal point is a point where exactly 50% of the bandwidth are given to both. Okay, this central black dot shows the optimal point. This 45-degree straight line, which shows a plot of allocations which are equal for user 1 and user 2, is called a fairness line. Okay, fair allocation, because there are only 2 parties. So every time you allocate something to 1, you also allocate the same to 2. But you cannot go beyond certain limit because your sum is 100. So you kind of limit that using something called an efficiency line, which is another straight line perpendicular to the fairness line. And that intersects the fairness line at the optimal point. Okay. So this is an intersection of the fairness line with the efficiency line. That is my optimal point. The question is, if you perform additive increase and multiplicative additive decrease, suppose your starting point, so you want to reach the optimal point. This is what you want. Okay, your goal is given a starting point in this space within this right angle triangle of 100%, 0, 100%. Any point of any line, any point, starting point inside, outside this right angle triangle, no point considering any point, because there is nothing more than 100% bandwidth for either 1 or 2. So we can keep ourselves confined to this right angle triangle. Okay. In this, given any random arbitrary starting point, can I settle at the optimal point? If you perform both additive increase and additive decrease, AIAD, you will perform a 45-degree straight line like oscillation across the efficiency line, like the one showed. This type of oscillatory traces will have a slope of 45 degree, but you will go outside the efficiency line. It won't make much sense, and again you will come back. Okay, and you will keep on oscillating. Now, what about the other? What about multiplicative increase and multiplicative decrease? Again, it will be the same, but depending on the multiplication factor B, now your straight line, now your slope would not be 45 degree, it will be less than 45 degree something, but again it will keep on oscillating. Okay, you will never be able to, means the moral of the story is, from any point inside this right angle triangle, it is not possible to reach the midpoint of this hypotenuse with any other scheme other than AIMD. If you perform AIAD, you will keep on oscillating, never reach this. If you perform MIMD, you will keep on oscillating and never reach this because your slope will be less than 45%. However, if you use AIMD, then it is possible. So you start. oscillating along the efficiency line. Somebody's microphone is on. Could you please switch it off? Hello, please switch it off. Thank you. Speak. You start 45 degree, but then you will come back because of the multiplicative decrease. When you have got back beyond the efficiency line, you will get a signal from the network, a feedback through your poor through this good put that your packets are getting dropped or you are not getting acknowledgements within the stipulated timeout is happening, etc. You will get a feedback and you will now roll back the sending rate by multiplying with a factor B. The moral of the story is that this coming back, this straight line always points to the origin. And suppose again you reach this point, again you perform a 45 degree slope increase, but then again you multiply by B and you come back along a straight line pointing to the origin. Again you perform 45 degree increase and again you come back along the origin. In this way you are guaranteed finally to settle to the more or less the optimal point. This is used by TCP. How is it used by TCP? It is used by TCP by controlling the size of the sliding window to control the sending rate. Okay, TCP uses this algorithm. Finally, TCP needs to work with some parameters, right? So other than this A, B parameters, finally, what is the impact on the implementation? Implementation impact is the sliding window length increases additively, decreases multiplicatively. Increases additively means so many packets can be sent out at one go, and decreasing multiplicatively, I will decrease my this thing window size. So earlier I was sending out maybe 15 packets at one go. Now I will send out 5 packets at one go. I will decrease it by 1 by 3. How A, B, etc. are chosen, etc. we will study later on when we study TCP. Any questions about this? Students, I am expecting one question which other times students ask. Every time I teach this, students ask. So I have considered AIMD and we have seen that it works. We have considered AIAD and MIAD. They do not settle to the optimal point, but this can, if you stop it, it will kind of settle at a point which is not the optimal point, something else, and that's not. I mean, and it will keep on oscillating if you don't stop. Okay. There is another option we have not considered.
MIAD.
MIAD. Multiplicative increase, additive decrease. Anybody has any idea what happens there? Multiplicative increase means now if congestion is not detected, you will have WT multiplied by some B where B is greater than 1. And additive decrease is you will have, if congestion is detected, you will have WT minus A, where A is some positive quantity. Well, if you accept so AIMD, okay, sorry, not AIMD, MIAD, multiplicative increase, additive decrease is a completely useless protocol, useless method. If you adopt that, something very strange happens. First of all, it does not settle at the optimal point. Secondly, it settles finally at either of these two terminal points, where either user A gets entire bandwidth or user B gets entire bandwidth. Okay, so this something very strange happens. And which one will it settle? At which of these 2 points will it settle? Depends on which of them initially had more bandwidth. So if it was on 2 side, somewhere in this half of this right angle triangle, it will settle here. If it is on this side where it was more on the A side, it will settle here. Okay. So TCP uses AIMD, details about A, B, etc. selection, details about the window control mechanism, about the round trip time selection, everything we will study. Window size advertisement, how does it tell the other side what is an window size, what is the segment of like the structure of a TCP segment, all of these things we will study from next week. Next week Tuesday is a holiday, so we'll have our class on Monday. So I'll meet you on Monday next. Probably we will have a class test based on this topic. I will discuss with Professor Sandeep Chakraborty and will come back to you. Maybe if we decide, because we are not meeting before next Monday, if we decide within this week, I will come back to you and inform you over email about this class test, if there is a class test. Okay. Thank you. And I'm now stopping the recording.